Okay, so
Are we doing all that?
Delta H.
Say,
Delta F.
put it in joules.
You
So
know you
you're
can
calculating delta S.
You guys know you could check me
But
back the book, right?
Do we have to
No,
go
no,
tonight
no,
for the
the
lunch?
analysis
Is it due
takes.
tomorrow?
I'm actually not.
If it's an odd number,
What
it's
is
probably been
complicated?
checked.
Yeah.
I
No, I
don't
didn't. I wasn't thinking that much. I
So-
put this in my bed, but
For
I can't
So you
remember.
wrote
I'm
this
just so
down.
sad right now.
Okay, so
Yeah.
the test overall of this is going to be on Friday. So,
Wait, Friday.
no.
Yeah, I'm not gonna remember it.
There's one new equation to learn.
I didn't.
It's all done. Yeah.
Okay, well, we better get it
This is
done.
crazy. It's
All right,
Well,
so let's talk about some big ideas on here, okay?
you came over? I know.
So,
Something popped in my head, I think that's right.
Fergus gotta look.
well,
Is that why we didn't know how to do it?
no, I gave you the right one.
I'm so confused. It's cool. I'm used to that in this class, this one.
I lost
No, we're good, we're good. Mine was just a little bit obscure. That's all, we're good. Okay. I just, a momentary panic of like, whoa, this is bad. Okay, so let's talk about question number, like for example on 47. So if you look on that one, so you've got for certain group, are as follows, all percent down, so how do you explain the trends in the delta S value? So what you want to look at on that one is that, and this is this whole idea of microstates and things like that. So basically, the more opportunities there are for things to get screwed up, the more likely things are going to get screwed up. So if you look on this question, you're talking about group 4A. So if you go down that group and they gave you the values of the entropy. Now remember, entropy has weird units of joules per mole Kelvin, okay? So, and that comes from the idea that delta S equals delta H, there's a negative in front of that, over temperature, okay? So remember, enthalpy, entropy, that type of thing aren't things that we can measure directly. But what we do is that we indirectly measure things, and then we infer from that the enthalpy, the entropy, and the Gibbs free energy. So as you go down, those electron orbitals are getting bigger and bigger and bigger and bigger and bigger. So basically, if you look at that trend, so the bigger that value of entropy is, basically the more things that can get screwed up. So imagine that this room was only the front half of this room, like I didn't have the lab in the back, okay? I couldn't have as much disorder because I just physically don't have as much room to mess things up, okay? But so they stupidly, when they built this school, said, hey, physics needs a big room. Let's give Burkamp a lot of entropy. I said, cool, okay? And so almost 30 years later, I have a lot of entropy in this room. So that's kind of the idea on that one. When you get to that question on 25, okay? So basically, the second law of thermodynamics basically says any spontaneous reaction increases the entropy of the universe. That's all you have to have. Then, if the entropy of the system increases during reversal, what can you say about the entropy of the surroundings? So here's the basic idea, is that you can't have an increase in one type of entropy without a decrease in the other one. And so the classic example of that is if you look at melting ice, okay? So if you look at melting ice, oh, okay, right. So when that happens, you're going to increase the entropy of the ice because you're going from a solid into a liquid, okay? So that's going to increase the entropy. But to do that, you've got to break bonds. Well, to do that, you have to absorb energy, and that energy has to be absorbed from the surroundings. So if you're going to increase the entropy of the ice, you're going to decrease the entropy of the surroundings. So if in a situation like this, if you can think this through, go, okay, hey, what's happening? Right, cool, we got this happening. Ice is going to melt. It's going to increase that entropy. Well, it's going to cool the liquid down, or it's going to cool the air down. That's going to decrease the entropy of the surroundings. So if you're going to decrease the entropy of one thing, you have to increase the entropy of the other. Okay, so that's kind of the trade-off that you're always going to make. So on 25, when I say, hey, give us a numeric value. So on 25, here's the basic idea, is that in a certain spontaneous reaction, so let's start with this idea. If you see that you have a spontaneous reaction, there's a couple of things that you need to focus on. One is that delta G is going to be a negative value. Okay, that's one of the most important things. And delta G is going to equal, or delta G, is going to equal delta H minus T delta S. Okay, one of the most basic fundamental ideas that exist in all thermodynamics and exist in chemistry. If you remember one equation and the subtleties of one equation, you remember this. So, when you see the idea that it's a spontaneous reaction, the system undergoes an entropy change of delta S of 42 joules per mole Kelvin. What can you conclude about delta S of the surroundings? So, if you look at this in terms of delta S of the universe, here's the other big one. You have delta S of the system plus delta S of the surroundings. Okay, it's a spontaneous reaction. So what do you know about delta S of the universe? What sign does that have to have? Positive value. So what you're given is that the system undergoes an entropy change of 42. So that's a positive value. So is the system increasing its entropy or decreasing its entropy? It's increasing. This would be like melting ice, okay? So the delta S for the system is positive 42. So these have to have opposite signs. So right away, you know, if the delta S for the surroundings has to be a negative value. So because of the fact that it asks for an actual value on this one, on, which one is this, 425, okay? So on 25, then that, whatever this is, a negative value has to be less than that 42. So it has to be a negative value, but it could be negative 41, it could be negative 40, it could be negative 39. Technically, it could be like negative 41.9. It just has to be less than, it has to be a negative value, smaller than 42. Okay? Does that make sense? Because all you have to do is create a positive delta S for the universe. And the whole key to that, and what you'll see is this, a lot of these are boiling down to like, is it a spontaneous reaction? Is it spontaneous at high temperatures? Is it spontaneous at low temperatures? Okay? You have to be able to read the subtleties of the tea leaves to figure out these problems. Okay? Got that? Cool. When you get to, like for example, 54, so there's a whole bunch of things that are important on 54. So first off, you got delta H is a negative 19.5 kilojoules. Technically, that's kilojoules per mole. The book got a little bit lazy and said, we're just going to put the kilojoules. Technically, that's per mole. Now, here's the story. Is Mother Nature going to like the delta H part of this? Morgan.
Yes,
Yes, why?
it's negative.
Which means it's endothermic or exothermic? It's exothermic. Mother Nature likes a hot mess. So as soon as you see the negative delta H, you have a fighting chance. this reaction, as soon as you see negative delta H, you think, wow, this reaction could at least happen. Now, if it had been a positive delta H, ooh, this might not ever happen, because Mother Nature doesn't like endothermic reactions. She likes exothermic reactions. So as soon as you see the negative delta H, you think, the reaction could happen. Not necessarily, but it could. Then you've got delta S is positive 42.7. Okay, so you got a positive delta S. So you have a negative delta H, which Mother Nature likes, and you have a positive delta S. Does Mother Nature like this combination? Why? Yeah, it's a hot mess. It's an exothermic reaction that's increasing the entropy. This is cool. This is in Mother Nature's wheelhouse, okay? So she's smiling at this, going, this is cool. I like this, okay? So is this reaction going to be temperature dependent?
No.
Because it's always going to happen, okay? There is no critical temperature, okay? The only time you have critical temperatures is when you have two positive values or two negative values. And here's the easiest way to remember that. If it's two positive values, remember, oh, hey, people that are positive tend to lift you up. That means you have to be above a certain temperature. If it's negative value, negative people tend to bring you down. That means it has to be below a certain temperature. Now, the other thing I want you to get out of your minds right now is that when you have two positive values and you talk about temperatures above a certain threshold, that does not mean it has to be like at the surface of the sun, okay? When we say it has to be above a certain point, that's it, okay? It doesn't mean that it's going to be at, 500 degrees Kelvin or something like that, okay? It just has to be above a certain temperature. If you have two negative values, it just has to be below a certain temperature, okay? So don't flip out and go, oh, that means it's really hot. No, it just means it has to be above a certain point. So, when you get to B, is the reaction exothermic or endothermic? That should be simple. Okay, there you go. Is it increasing the disorder? Okay, look at the sign of delta S. So then you got to calculate delta G from the reaction at 298 Kelvin. So to get that value on C, you're going to use O. Delta G equals delta H minus T delta S. Now, here's what you have to be careful of. That delta H value is in kilojoules per mole. Your delta S value, if you look at that, that's in, technically, joules per mole Kelvin, okay? So you have to make a decision. Either convert the kilojoules to joules or convert the joules to kilojoules, okay? I don't care. But what you cannot do is blissfully take that value of delta S and plug that in and use it straight up as it is. You have to pay attention to the units, okay? So if all goes well, if you're in kilojoules, okay, you should get a value that's around negative 30, okay? So now, D is somewhat of an odd question. Do you even really need to ask D?
No.
What?
Because you kind of answered it with your delta G.
Yeah, I mean, well, and it's always going to be spontaneous, okay? Even if you let the temperature drop to zero, even you go to absolute zero, you're still going to have a negative delta H. So it's still going to happen even with that. So anyway. On 53C, because that's the only one with like a numeric value, that should be around negative 10, if you're in kilojoules. When you get to that question on 51, so all I'm asking you on 51A where it says, express the change in Gibbs Free Energy in terms of enthalpy and entropy of the system, all you have to write down is this equation. Delta G equals delta H minus T delta S. That's all you have to write down. Don't make it complicated. Literally, that's all you have to write. So when you get to that question on B, on 51, so you got the value of delta G is positive. What can you conclude? Oh, well, you get a positive delta G. Is it spontaneous or not spontaneous? Not spontaneous. Then, on the next part, it says, what's the relationship between delta G for a process and the rate at which it occurs? Now, let's talk about this. All delta G tells you, if it's positive or negative, is if the reaction is going to take place, okay? That's all. It doesn't tell you anything about the rate at which the reaction is going to happen. So that answer on 51C, where it says, hey, what is the relationship between delta G for a process and the rate at which it occurs? There is no relationship, okay? It has nothing to do with each other. You could have spontaneous reactions that occur very slowly. You can have spontaneous reactions that happen very quickly. But if all you're given is the value of delta G, you cannot look at that by itself and determine the rate, okay? And you all have seen that. Like, remember we did the iodine and the acetone lab. You guys cooled that down? That long, like 20 minutes, okay, to do that reaction. Yeah, it was spontaneous. There was a negative delta G, but God, it took forever, okay? So, good with that. Any other questions on the lab, or on this assignment?
24B.
Huh?
24B.
24B?
Yeah.
Okay. So, that's just kind of a stoic problem. So, calculate the delta S when 15 grams solidifies. Okay, so let's talk about 24 and the subtleties of this. So, you're talking about it freezing. So as soon as you see something freezes or boils, that means that it's temperature dependent. So part of this code is, if you see the word freeze, if you see the word boil, if you see the word condense at a specific temperature, that means it's temperature critical. That means you're going to have a positive delta H and a positive delta S, or you're going to have a negative delta H and a negative delta S. So as soon as you see those key words, and you see, hey, this happens at a specific temperature, that means they're either both positive or they're both negative, okay? Otherwise, they wouldn't have to have that temperature. And remember, that temperature comes from the idea that delta G equals delta H minus T delta S, and at equilibrium, delta G equals 0. So if you move that over, you get temperature equaling delta H over delta S. So this is why, and I'm telling you, the more ways that you can think these problems through, the better off you're going to be. So what I'm saying here is that when you've got that positive delta H and that positive delta S, okay, that's the only way you can produce a positive temperature in Kelvin. Or if they're both negative, you can produce a positive temperature in Kelvin. But if you have one that's positive and one that's negative, mathematically it won't work, because you can't produce a negative Kelvin, okay? So this is why, being temperature dependent, where you reach a point of equilibrium, they're either both positive or they're both negative, okay? It's the only way it works mathematically. And that's the only way you can let delta H or delta G equal 0. So, with all of that said on 24, so delta H fusion is 2.09. Here's the story. When you have that positive 2.09, is this an endothermic or exothermic reaction? Shaden. Okay? Now, and here's the reason why. You say it's endothermic and because of the talking about this fusion process. So, it's endothermic. Which direction is the energy going to flow? Into it or out of it?
Into.
Into it. Okay, great. Because you're talking about melting a substance. Oh, you have a positive delta H because you have to put energy into the system. Cool, makes sense, all right? So, now, at its normally point, delta S is positive or negative. So, again, it's temperature dependent. If you have a positive delta H, what they gave you, and it's temperature dependent, what has to happen to this? What has to be the sign of delta S? Positive, okay? Because that's the only way it works, all right? So then, on the next question,
Bird.
what? Oh, I'm sorry, let's talk about the melting point. My bad.
I was gonna say, yeah, on A, it says it solidifies. I thought when we went down
Okay,
to
it
states,
is. I was thinking of the melting process. Okay, my bad. I was thinking of the melting process.
Negative.
Yeah, it
Do you
is.
have a negative?
Yes.
It is. I was thinking of the melting process. They're talking about the solidification process. Okay. So yes,
It's a negative.
it's going to be a negative value. Okay, it's going to be a negative value. Okay. My bad.
You're okay, we're kids.
It's okay.
But
I
you
thought.
We forgive you.
You were just checking if we were paying attention.
Oh, and
Bird.
you were, and I appreciate that. Anyway, so on 24, you've given the grams. So make the stoic work out. What are you going to do with the grams of cesium? Turn it into moles of cesium. Then, if you look at that, you've got 2.09 kilojoules per mole. So then from there, you can find your number of joules involved, okay, because it's kilojoules per mole. But what it's asking for on 24b says calculate the value of delta S. So delta S, remember, is negative delta H over T. So once you get that value of delta H, then you need to take that value and divide it by that temperature. So your answer to 24b should be very much less than 1. 0. Around 0.8.
Okay.
Around 0.8. Okay, are we cool?
Positive, negative point. Negative, right? Because it's negative.
Yeah.
All
Which
right.
one? Okay, so hold on. We're good.
Pretty sure those do.
So on 44, which one to have this higher standard molar enthalpy? So basically, if it's not balanced, then that's going to be like more entropy.
Okay, so it'd be the second one.
Propylene.
The propylene, yes, okay,
Yes.
cool.
Now, don't hold that in yet. There's a couple other questions that I want to add to that assignment, okay? Just hold on to it. Just hold on to it. Just hold on to it. Actually, that's just going to make things complicated. Just go ahead and hand that in. I'll just grade this separately.
Hand it in.
This is bad.
Bye.
Can you go like old class?
I'll hold on to it.
Okay. Yeah, just go ahead and staple it. Go ahead and hand that in. I'll deal with that.
She really just did that. Like, okay, like, Loki felt like that before, but I don't think I've ever actually done it. I feel
Sitting on
respectful.
my coffee table. No, there's still 2 more batteries in it. Wait, there's a battery. I don't have a charger for it. They're the same, like, batteries from sophomore year though. But I really need one of more batteries. I was like, no one ever even having it for, like, homework lessons. Who does that?
I do. Have you seen Scary Movie? Right in.
But I saw that battery again. That's a good question.
You did a good job.
Oh, there was a woman. I know, crazy.
That's crazy. I would not trust a woman around my nose.
I mean, she looks like a man.
Around your nose.
Nose.
Oh, I thought you were saying your nuts.
Hey, I'm gonna be honest, the guy did my nose.
I have